All right, we're back. We are Game 2005. That's Game Physics in the fall 2018 semester, and it's week, 13. And we're talking about collision detection in 3D today. So again, I'll put these slides up later on, but I wanted to include some more code as well for you guys, right? So that's why I kind of created these slides late into the night. that's where the force. So they may not be perfect, but please bear with me. All right, so we're going to be dealing with different geometric types. And what I mean by that is when we start doing collisions, especially in 3D, we got to think about simple types like line segments and planes and boxes and those kinds of things. So those are very basic types. And I think if we don't have those things, then there won't be enough tools for us to do proper collision detection in 3D. So let's talk about line segments. Now I'm actually including some code in here, and let's see if I can actually maximize the screen. Because I want to talk about this stuff. I want to talk about this structure stuff. So we've got the structure now. It says vector 3 here, but we've been using the GLM graphics library, right? So math library. So vector 3 would be a vec3 when we're dealing with it, right? But it's the same thing. Think about this as pseudocode again. We've got a structure called line segment. It has a start and an end. It's pretty simple. The start and the end, in this particular case, because they're vector 3s, are three-dimensional points, x, y, and z, right? So you've got two points to start us off, and really what we're talking about is the length of the line can be determined by the start and end points. Okay. Lines are really, really important because once we have a line, we can do things like cast rays, right, which are really interesting. That'll help us do stuff like detect, like use some kind of artificial intelligence potentially. One of the things I always like to do when I first start off a game and I have a simple enemy is create rays that they cast, right? Lines. So line segments actually that they use, right? And the line segments can be like literally, not too many rays, by the way, because too many rays becomes crazy. But you want to kind of do intersection between a line and different things. If I have a line and I'm casting a ray, I can do things like fire a bullet in a straight line, or, different kinds of detection, like I'm on the ground, I'm grounded when I'm on a platform. Those kind of things. My enemy can see you, right? Has line of sight, those kind of stuff. And once an enemy can see you and I can draw a line from the enemy to you, then I can fire bullets at you and those kind of things, right? So line segments are like, although they're very basic, are like totally required knowledge how to do them. So that is why I've included it in these slides. So one of the things is we've got this line segment and we want to find a point on the line segment. This is interesting. So we pass in a floating point, a point t, right? A number. Think about t as a position or a ratio of the line. So if I put in something like 0.1, it's a floating point number, then the point will be closer to the beginning of the line, right, as opposed to the end of the line. Okay, that's what this equation does, right? Actually, if you think about it, if we take this one step further, we can create things like linear interpolation, which is we also call lerping. We can lerp between one line and another. Let's take it even a step further. And if we think about the start and end points as not points, but actually colors. So instead of X, Y, Z, we're looking at RGB. Now we can linear interpolate between one color and another, right? We can create a color ramp, if you will, right? So all this kind of stuff, we start off with lines. Lines are really, really important. A lot of times in math, we always talk about a line is the slope of a line, mx plus b. And you know what? In trig this year, we kind of talked about something like that. Guys, mx plus b for lines, for programmers, for developers, absolutely useless. It'll actually throw you right off. Don't use that, ever. It's better to do this, right? Why is that? Because once you start doing a slope of the line, what's the slope of the line in 3D? It'll totally mess you up. You can't do a slope of the line, right? Not like that. So, there we go. So again, I highly recommend thinking about a line segment in terms of this, which is where you have a start point and an end point, And I want to find a middle point somewhere in the middle of the line based on this floating point number, and I'm gonna be able to figure this out. All right, so lines. Sometimes we also want to find the shortest distance between a point and a line. Okay, so I got a point in space, and I want to find, I got this line, and I want to find the shortest distance. There's so many applications to this little thing. And again, I was mentioning earlier before we started broadcasting that I think, it's my opinion, that we don't have enough math, right? Kind of thing, right? And I know people hate math. They're like, math is suck. You know, I don't want to do that. And you know what? It's too mathy for me. I don't want to do any mathy stuff, right? When I'm programming, I just want to do Unity and drag and drop. And, you know, that's fine. But there's a place for people who just want to do Unity, drag and drop, and maybe even Game Maker. But, you know, but that's not what we're doing here, right? We're teaching them how to be game dev students and furthermore, progress in your careers. And we need to know a little bit about math in order for us to do some funky stuff. And here's an example of a couple of situations. We have three cases here. We have a line where the point we want to figure out is way on the left. Okay, so it's outside of the line, but it's over here. There's one where the line is, you know, the point we're looking for is way on the right, right? And there's one where it's perpendicular to the line itself. So those are the three cases that we want to kind of detect the closest point, right? Where is it? Is it closer to B or is it closer to A? What's the closest point on the line? So we talk about this, and I kind of detailed it here in three different cases. And this is coming from a great book about C++, you know, creating games in C++, 3D, right? Which is really cool. I didn't make this stuff up, but I like it because we use the dot product, right? The dot product between the 2 points, right, in three-dimensional space also works in 2D. That's why I'm bringing it up too. It can also help you with some of your stuff you're doing coming up. Where if the angle is between A and B and A and C is greater than 90 degrees, so let's go back to that. What do I mean by 90 degrees? First of all, in computers, how do I measure angles? This is really simple, but do I start like here and go this way, or do I start here and go this way? From B to A or from A to B? How do I go? B to A, this kind of goes up this way, right? So once I start going up this way, we can see that the angle on this end here, if my character starts here and he's looking to from A to B, right, then he's actually looking at the 0 degrees area, right? This is where 0 degrees is, and this is also east from a a kind of a direction perspective, right? So we got east, and then we look up here. Once we move this way, we're going north. That's 90 degrees. So when it says greater than 90 degrees, it's greater than this part. So if it's greater than 90 degrees, some angle greater than 90 degrees, you have this first case, okay? If it's less than 90 degrees, right? Now, this is interesting. This is kind of, okay, so I'm going this way, but now I'm going actually this way, right? So this is kind of an interesting case because I'm starting here, right? And if you notice, right, if last time I started here, I said, okay, so here, we're going to go here. But this one, I'm going this way around, right? So it's almost like I'm at 180 degrees and I'm moving back. So it's less than 90 degrees, actually, if you think about it. So if the line starts here, this is 90 degrees. Again, 90 degrees. This is 0. So this would be less than 90 degrees from this point. Yes. Is that a hint? Or okay, no problem. And this one would be where you're inside the, it's not, it's within the perpendicular to the actual line itself, right? All right, so you have these two easy cases, right? Where it's greater than or less than 90 degrees, right? From the other way around. And then you use the dot product, right? To determine whether it's one or the other, right? The final case, again, you draw a line segment from A, B to C that's perpendicular, which means at right angles, right, to A and B, and the distance of the new line segment is the minimal distance between C and A and B. So, so that's the three different cases that you have for lines and points. Without doing all the mathy stuff, by the way, I've left some of the mathy stuff out because then I can show you equations and blah, blah. Not going to help you programming in whatsoever. I just want to think about these three cases. That's more important to me. This idea of a scalar projection, we can use code like this. And again, I want you to, let's just zoom in here to this point. I want you to think about this. We have this line segment. We're creating something called minimum distance squared, right? What minimum distance squared is, I want you to think about this. I'm passing in a vector, so vec3, which is a point, and I want to know what the minimum distance squared is. Why am I using minimum distance squared and not just minimum distance? If I want to calculate this on every frame, right? Square root, again, bad, right? We don't want that. We want to take the squared distance, which means we square something, but no square root. We don't want to use square roots. And when we square something, we do like a times a, b times b. We don't do it, power, again, just to reiterate. So we have these things where basically what we do is we construct vectors. So here's 4 vec3s in this particular case. So AB, vector AB is start or end minus start. That's what the difference. And how do we do this? Because end and start, if you think about this, like where are these coming from? But if you go back a couple slides, then you can see that M and start are part of the line segment, right? End and start, a line segment is made up of this. This is part of the properties of the line, right? And what we want to do is basically take that stuff, right, and calculate AB. And AB would literally be, don't do that, would literally be this idea of AB, the distance, this kind of stuff. We want to find the distance between these two areas, and we're taking one, subtract the other one. It's like simple as that, right? Okay. So again, I'm just going through the code a little bit just so you understand where it's coming from. Okay, what about BA? So BA is the other way around. And you think it's as easy as doing the same thing, but actually remember that vectors have magnitude and direction. And that's what we want to do here. We take AB and we multiply it by -1, and then we get the opposite direction. That's all we're doing here. All right. AC is whatever the point is that we're trying to find, minus start, and BC is whatever the point is minus the end, right? So we want to find which of these 2 points is greater. And we have these 3 cases. So case 1, C projects prior to A. So that means that it's going to be somewhere before or greater than 90 degrees, right? So if that's true, we say something like if vector 3, if the dot product, and by the way, this is just, think about this as pseudocode. We have dot product and cross product that comes with the GLM library, right? It's actually GLM, it's part of our core. We'll talk about that in the lab. But if I want to take the dot product between these 2 vectors, A, B, and A, C, right? Then if it's less than 0.0, so less than 0, then we know that this is the case. We have this first case where we were going to return the length squared distance between A and C. So, that's going to be the answer. Otherwise, we'll do the other ones. Okay, so that's the way we figure out which is the closest distance. If you notice, case 2 returns BC. Now, this is interesting. Case 3 is when it's neither one nor the other one. So it's not like it's where BC is less than 0 or whatever. Here's the one where we say, well, if anything, if it's not one of these 2, then it must be that the point is within or perpendicular in some ways to the line. It's hovering. Think about the line, and the point is hovering above the line somewhere. Okay, that's what it is. It's projecting onto the line, not next to the line. Okay, so it's on the line itself. If that's the case, then we're going to take that point and find the perpendicular distance between that point and the line segment. Okay, so that's the closest distance. Okay, whoa, why do we care about this? Guys, there are so many applications to line and point. It's amazing, right? Think about this. I want to find, there's a bullet, okay? Point, whatever. Because a bullet, all we care about for a line and point, if you think about this, is just the center of mass, right? Just like we've been talking about all semester, really. It's a particle, right? I got this particle, and it's speeding towards a line, right? I'm going towards a line, and I want to know what the closest point of that line segment is. Line segment could also be an edge, right? I have a different kind of shape. I might have a shape that has, some kind of weird, I don't know, a different polygon, right? Whatever it is. Or maybe it's a polygon collider, some kind of mesh collider that I'm creating, right? And I want to find what the closest point is to that solid line segment. I can figure it out. I know which one it is, if it's A or B or somewhere in the middle, right? So interesting. And you can actually project where on the line you're going to hit, right? If you think about this, by just knowing that the squared distance, or if you're going to hit the line at all, or if you're going to miss, right? So it's kind of interesting. This is I think one of the simplest and yet most useful things you can know. All right, next one, plane. And again, we're looking at 3D collision detection today, which we can also use in 2D. All we have to do is just remove, for the most part, we can move one of the axes, and then all of a sudden now we're in 2D, right? Okay, so we got this plane. It's a flat two-dimensional surface. A lot of times we think about a plane, especially in games, as triangles, right? Like a bunch of triangles on the screen, and we want to find the normal from the triangle, which is the perpendicular point from the triangle's surface, right? That goes 90 degrees outside of the triangle, right? And we can kind of think about a point as some kind of point on the plane. That's P. N is the normal to the plane, and D is the signed minimal distance between the plane and the origin, right? Wherever that origin is, the origin of the world. Okay. Once you have that, once you have the signed distance, and the reason why would you care about the origin? Because then it gives you the direction and the facing of the plane in three-dimensional space, right? So this is really cool. So once we have the idea of planes, now we can make three-dimensional objects made of a bunch of triangles. And triangles are one of the techniques we use to create 3D geometry, right? Whether it's hard surface modeling that we use, or we want to use organic modeling and create models that move around, and stuff like that. Triangles are kind of our minimum component. All right, so here's an example of a plane. We have a structure of a plane here. We have a vector 3, which is the normal. So that's a point that's outside the plane. And D, which is the minimum distance between the plane and the origin. All right, so that's really the structure for the plane. What we want to do is we want to find a triangle that lies on the plane, and we can construct this triangle by using 3 points, right, in three-dimensional space. So here we have the plane itself. Plane, it has a function called plane, and what's this function? It's the constructor, right? Plane. And if you notice that it's a vector 3, it takes 3 arguments, a vector 3 that's A, another one that's B and C. So when we construct a plane, we can do it with these 3 points, and then with these 3 points, we can construct a triangle, which is really the dot product of we create the dot product in the normals. We figure out the normals by using those 3 triangles. And remember when we use a cross product, you guys remember what that is? Were you ever taught cross product? Hopefully you were, right? It's using the right-hand rule, right? So basically what you're doing is you kind of use your hands to form kind of something that looks like a manipulator that you use in Unity or in, I don't know, Blender, if you're a Blender artist, or Maya or Unreal. And that manipulator, usually you have some arrow that points up. In Blender, it's Z up. In Unity, it's Y up. I think it's Unreal, it's Z up too, right? Yeah. So you have these things, and you have one arrow that points into the screen, another one that points to the right, another one that points up. And depending on how you hold your hand, right, you have the rules that kind of point in and out. So that the cross product is usually the one that goes into the screen if you have a two-dimensional space like this, right? So I was going to hold my hand up, and where my thumb is on the x-axis and my forefinger, my pointing finger, is up towards the y-axis, then my other, the FU finger, right, the middle finger is pointing into the screen, and that's the z-axis, right? Typically, that's how we use it, right? That z-axis is the cross product of x and y, right? That's how it works, cross product. So you can figure out the normalized, vector, if you will, the normal to the plane by using the cross product. And that's really what we do with cross product. Okay, and normals, by the way, are super important for lighting and all that kind of stuff. So we need to understand the normals, where the normal is facing, because the normal is going to receive light and shadow and all that kind of stuff. And it's going to change the surface of all the pixels that are on the same plane as the normal, okay? So if there's a plane, in this case, we're talking about triangles. We have one part of the plane, which is a triangle, and all the pixels facing that way are going to receive light in the same way for the most part. Okay, and then that's it. That's kind of how do we define a plane? Any questions around this before we move on? Because I want to talk about bounding volumes in a second. So this stuff we've kind of covered, but not really covered, and that's why I wanted to bring it up in 3D. By the way, we're going to have a chance to practice some of this in lab. Yeah. I know. Yeah, I'm going to put it up very soon. Yeah, I do apologize. Yeah, so bounding volumes. Let's talk about this. So we have these. We want to create bounding boxes or collision detection. Unity uses bounding boxes, bounding spheres, all that kind of stuff as well. I'm just giving you an example of Unity. And by the way, we use this for the most part to make it easier for us to detect collisions. And we talked about that last week, where we have some kind of bounding volume in 2D. We use primitive shapes to kind of bound an object. And when we do that, we get the ability for us to kind of have easier collision detection. It's just an easier way for us, right? And we also talked about last week, what is good enough, right? We talked about maybe, if we want to be super precise, that's bad, right? Because it can lead us down into temptation, and we'll be back, we won't be able to, kind of finish our game because we want to do, super precise collision detection. And yes, if you're doing a simulation, a scientific simulation, that might be good. However, if you're playing a game, then you got to find what's good enough. Here's an example of a bounding volume, a sphere, the most common one, believe it or not. Spheres and boxes, or prisms, three-dimensional prisms, if you will, are the most common bounding volumes that you can use, right? So a sphere is super easy because we have a center, so some kind of point in the center, and a radius. Those are the two things that a sphere has. And when we went back last week, we had a circle-to-circle detection, where we have some kind of center and a radius. But in this particular case, the radius is in 3D. Center's in 3D. The radius is a floating point number. So we can kind of define a sphere. Once we have the sphere defined in memory, then we can do a bunch of stuff with it. So we wanted to fit around a bunch of objects as an example. And the challenge with the sphere is it works great with spherical things, like I talked about last time. Doesn't work so great with, squarish things, right? And I talked about that last week as well. Example would be this. You have a bunch of different spheres. Think about this again, and this is not good, right? Why? Because I'm here. Let's say I fire in here. This is my little laser pointer is my, I don't know, like some kind of sword swinging. I swing a sword in here. All of a sudden, boop, the character gets hit. So there's a false positive. Or, like I like to say, there's no visual collision, but there's a logical collision, right? So this is bad. This is good, right? Because now it's something that's spherical. A ball, something is not great. This is not great. It's better to use a prism, some kind of rectangular bounding box, because of this, and this, these areas, right? Not bad, though. If you tighten up the sphere a little bit, you might lose some fidelity in terms of the outside. I mean, a square might do this, or some kind of rectangle might do this better. I'm not sure. But this isn't bad if you tighten it up a little bit, because it's kind of, circular. But this is really bad. Okay, so just the idea of what kind of bounding volume you want to use. Yeah.
What about if you have something like a car tire? Are you able to use something like a cylinder, or would you have to?
It really depends on what you're doing with it. Are you really trying to detect collisions with a car tire? Sometimes, it depends on what kind of simulation you're doing. So yeah, I mean, using a sphere would be bad. Could you use a cylinder like a primitive? You could, but now you're talking about a different kind of how would you do collision detection on a cylinder? You have a circle, basically, with a height, right? And as long as you can figure out the primitive formula for any of those shapes, yeah, cones, cylinders. Cones are great for lighting, right? I want to cast light, and I want to make some kind of spotlight. I use a cone. There's the volume that I want to use, right? It's a primitive shape. So yeah, yes, you can do that, right? But remember, the effect is what you're looking for. Like, what is the effect? Are you looking for the car to roll, really? Or do you care about the car moving with some kind of animation that looks like it's moving, that has some kind of effect? Sometimes, the simplest things are the best things, right? So the car is moving, it's animating, and you're moving it at a good rate. There's no IK, inverse kinematics, that are moving the car, right? It just looks like it's moving properly. That might be better than I want to collide with the ground, right? And that's because that's a whole physics simulation afterwards, right? Or they can be. Okay, so we talked about axis-aligned bounding boxes last week in 2D. What about how do we calculate those things in 3D? That's a whole other thing. There's actually a few other things to think about, but one thing is when we look at AABB, here's the structure for it. So we have two vectors, right? In this case, it's a vector 3. We have the minimum and maximum volumes, okay, or positions, if you will. Now, that's interesting because that's like the top left kind of corner. In 2D, it'd be top left, bottom right, okay? But what about in 3D? How the heck do you know what min and max are, right? Again, it depends on the orientation of the object relative to the origin, okay? So that's what it comes down to, right? And depending on how you want to look at this, axis aligned means aligned to the world axis, X, Y, and Z. And so you have to figure out how that works out from a minimum maximum perspective. So this is interesting. We can also construct AABB from a bunch of points, right? When we make a bounding box, remember, we're making a bounding box, we're actually making a cube or a cube projection. That's what we're doing from a series of points, right? And here we have, as an example of, I want to update the minimum and maximum points on, for example, on an AABB, right? And where we can say that I have a vector 3, and a vector 3 has X, Y, and Z. So this is the point that we're looking at. We're actually creating a vector, and I mean vector as in like the STL, standard template library vector, or an array of points that exist on the surface of the box, right? So if you look at it that way, if I go back, so remember that we have min and max. Min and max are two three-dimensional points, right? Okay, and here we have update min max. So I have a point, right? And then I say, okay, min X, and I want to do the minimum. When I use minimum, it's basically I'm clamping, that's what I'm doing, between the minimum X and the point X. What's the minimum value, right? This point on the line, where does it belong? Is it closer to this, the minimum value here, or where is it closer to? And then basically what I do is I update each of the minimum and maximum values, right? So X, Y, and Z minimum, X, Y, and Z maximum, depending on where that point is relative to the AABB. This is really key, right? Once I have that knowledge, which one is closer to, if you will, by using this clamping method, right? And how does clamping work? I would say if I was going to find the minimum, I would take these 2 points, these two floating point numbers. So let's say, for example, min X is 1 and point X is 2. Which one's minimum, 1 or 2? Well, it's 1, so we take this one, right? If this one was minimum, then we take this one, depending on which one it is, which is minimum, which is smaller, right? And the same thing we do for all these points until we have the minimum and maximum vectors mapped out. Now, we just don't do this one time. We use the update points, right, to create a, and again, what it says is assume points itself is a standard template library STL vector of type vector 3. All right, so we have a vector 3, or in our case, it'll be a vec3, and we have this thing called points, right? So we say that we want to pass in, let's think about this as a function. It returns an AABB, right? That's what it does, right? And we pass in 2 points, points 0 and point 0 in this particular case. This point is what we're passing in. And then what we're doing is we're updating, when we do this, points and 0, 0, what are we doing this when we pass it into a box like this or some kind of a function? We have a reference to points. That's what we're doing, right? So now we're seeing this a for loop that goes through each of the the objects that are inside the vector, the array, and what they're doing is they're updating each of the points that are inside of the array. That's what we're doing here. We're not adding new points to the array. We're just updating them based on the point that I'm looking at. So point 0, point 1 actually all the way to point X, where X is the maximum size of the number of points in the array. All right. So one of the things we talked about here is, an AABB to work properly, it must be parallel to the axis. So in order, so it has to be like this or like this. And even when it's like this, we just draw another box. That's what we're doing. That kind of meets the thing. We don't rotate the object, right? Because once you start rotating, now we're getting into like weird rotational mathy stuff. The mathy stuff people hate. We're probably using quaternions and those kind of things to rotate it in 3D. So you don't want to have gimbal lock and all that kind of stuff that can occur, right? And that becomes way more challenging. But here with AABB, we want to keep it really simple. So we just draw a bounding volume that goes around the shape so that it encompasses the shape minimum and maximum values, right? So that's what we're doing here. So if there's a point that's part of this shape, a humanoid shape, then we try and draw the bounding box so that it meets the requirements of these points. Okay. So they talk about here how to construct an AABB after rotation, because what happens is, so what do we care about bounding boxes? Remember, bounding boxes are one of the simplest forms of collision detection, right? We have a draw bounding volume around an object, right? And now it's rotated in three-dimensional space. Well, guess what? We've got to change the size of our bounding volume when it rotates. How do we do that? So there's a method for here. When we rotate something, again, we pass in a quaternion, right? Remember I talked about quaternions? And I'm not going to go through the code here because it's outside the scope for what we're doing. But if you wanted to try and do this, you pass in a quaternion, and this would be basically a rotation. So it's not an Euler rotation, it's a quaternion, right? And once you pass it in, you can figure out from the rotation that we're getting in how to figure out the new bounding volume, right? So basically this method here reconstructs the bounding volume based on the rotation of the object that's inside. Okay, so that's really how it's done. Okay, how about oriented bounding boxes? So bounding boxes that are not aligned to world space, if you will. So now this becomes a more challenging structure, right? Again, one of the things you notice is that we have a center, right? So for the bounding volume, and we also have a quaternion, which is the rotation. We keep track of the rotation. My friends, I also, recommend using a matrix here as opposed to just a quaternion by itself. I think quaternion is okay, but matrix might be even better, right, in terms of holding the actual rotations and everything else in three-dimensional space. Also, vector 3, which is the extents, and the vector 3 itself would have width, height, and depth, right, as the extents of the oriented bounding box. So if you have that in the center and you have a rotation, you can figure out where the bounding volume is going to be. Guys, this is a nice idea, but it's more computationally expensive to use an OBB, right, than an AABB. Just letting you know, right? So that's why it says here, although it's tempting, the downside is the collision computations are far more expensive with OBBs compared to AABBs. So this is definitely a way you could do it. Not recommended. Okay. Capsules. Oh yeah, this is like so common. We see this everywhere. And if you notice why the capsule's got the shape is, it's a pretty good shape for 3D characters, first-person perspective kind of, or third-person perspective objects. And notice the sphere on the bottom. We've got the sphere on the bottom, and that means there's a minimum contact point between the sphere and, let's say, a plane that's on the bottom here, right? So if, let's say the character is walking on a plane, you've got the sphere. That means there's only a contact point right here. And he can have whatever animation he has within this bounding volume, but his locomotion is single contact location with the plane. Why is this good? Am I grounded? You might notice this sometimes too. You have a person, or you might see a character. He's on the edge of a cliff, and one of his legs is kind of hanging over, and he's not falling over because this is what he's doing, right? He's got a thing. Now the better games can calculate if he's actually, it's not just if his legs are in a different position. They can calculate that he's going to fall over, or the slope or whatever. But in this particular case, this is a very simple way of calculating a bounding volume for a humanoid character. So again, we have this structure, capsule. I think it's a very useful collision detection structure because we have a line segment, which we talked about earlier. So we have some kind of line segment called segment, and then we have a floating point radius. So how does this work? So I have a segment that goes from here to here, and then I have a radius at both ends. There you go. There's your capsule. I mean, it's really simple. It's that simple. The radius doesn't just go like this, but also goes like this, right? So it wraps around the cylinder this way. It's almost like I've got a cylinder and two spheres at the end of the cylinder. That's what if you think about this, right? So kind of a very simple thing when you have a radius and a segment. Okay. The other thing it says here at the bottom, which is kind of key, is a capsule can also represent a sphere moving over a set period of time because there's a start point and an end point. So think about this as something called a swept sphere, which we'll talk about later on, right? Swept sphere. Okay. Convex polygons. So we have a polygon, and it says recall that the polygon is convex if all interior angles are less than 180 degrees. All right. So interior angles. That's convex, right? Not which is kind of interesting. And you can represent a convex polygon as a series of or a collection of vertices. So you have a bunch of vertices, and then I just connect them all together, right? And there's your polygon. So I have this standard vector. Again, think about this as an array, right, with extra functionality of type vec2s in this particular case. And we have all these vertices. Now, if you were going to extend this is a two-dimensional polygon. If you were going to extend this to be three-dimensional, it'd be a vec3. So you have a bunch of vec3s, right, vertices in three-dimensional space, and now you have a three-dimensional polygon, right, whatever that looks like. But if you're going to go there, then you might as well, you're also going to have most likely a bunch of triangles. Again, you're going to figure out the planes, each of the polygons, faces, and so on, right? Polygonal modeling uses this kind of equation in terms of figuring out how many polygons we have, for a particular structure. Okay, so here we go. It says they should have a set ordering such as clockwise or counterclockwise along the polygon's edge. And then without some kind of ordering where things are ordered in a clockwise, like when you actually load the vertices onto the polygon's vector being the array, standard template object, then at least have some kind of structure to it. Don't just like randomly put vertices in place, or else how are you going to do intersections? Like you don't understand how to do that, right? So that's what it's talking about here. Are we good with these are basic shapes and some basic tools before we get into intersections in 3D. Are we good with this? Everyone's nodding their head and saying yes, but actually, when it comes down to doing this stuff, it's a whole other, thing, right? Let's talk about intersection tests. So there's different kinds of tests. We can say that an object contains a point. That's the first kind of test, right? So does the sphere contain a point? Does the circle contain a point? That's a test. That's really good. That's really good to know, right? Why would that be really necessary? What about in 2D space? Does a rectangle contain a point? Why do we care about that? Button events. If I want to hover my mouse over a button, X and Y, and my X and Y coordinate is inside of the box. So the box represents the button, right? If it's inside the button space, hey, I have a click or a hover event or whatever I'm doing, right? Yeah, that's one application of it. Okay, so then the other one is two different types of bounding volume. So I have, let's say, a sphere and a plane, a sphere and another sphere, a sphere and a rectangle. How do I do those kinds of collision detection? What's the best way of doing those things? So that's the second one. The other one is dynamically moving objects, bullets. How do I detect collisions between bullets and something else? Okay, so those are the three cases. And again, this is all in 3D. All right, so contains a point test. This is the first type. So when we say contains points, so a sphere contains a point. How do I figure this out? So I know that I'm going to have the sphere itself. I have the sphere structure, and I pass in a vec3. This could also be a circle endpoint if it was a vec2, right? And then what I want to get is the distance squared between the center and the point. Now, again, we don't want to use square root. So what we do is we say, okay, what's the distance? Now here, in this particular case, if you notice, I have this, this is pseudocode again, where length squared is part of a vector3 or a vector2 object, right? In our case, it may not be. We may not have a length squared method. I'm sure we have something like that in GLM, but it's not the distance. We don't want to find the square rooted distance, you know, the Pythagorean distance or Euclidean distance between one and the other. We want to find the squared distance, which is no square root. And then what we do is we return if it's true or not. That's all we're doing. So we're saying, hey, if the distance squared is less than or equal to the square of the radius, remember, we're comparing squares with squares, so we're good, right? If I wasn't doing this, if I was going to get the actual length, then I would compare it to the actual radius. So length versus radius. If it's true, then I have a collision. I have a detection. That's collision detection right there, right? Is a point inside of a sphere, right? Is a point inside of a circle. Okay. Okay, how about AABB contains the point? So I have some kind of axis line bounding box. I want to see if it contains the point. How do I do that? We kind of talked about it last week where we said the minimum maximum values, right? The width and the height. We have taken those 4 values. If we're doing it in 3D, however, we need to do 6 values. That's all it is. So we have if point Y, we get a point we want to compare with. And what we say is if, you know, the outside, right, whatever that outside point is, right? So here's an outside point, true or false. If outside is equal to, you know, is point X and is less than, and then if you notice, there's a bunch of all these points, or, right? So it's comparing if it's outside or not, if it's true or false. Okay, so here's the first one. The first test is point X, so the X coordinate of the point is less than the minimum value of X. If this is true, remember, it can be any one of these things that makes it true, right? That's what you're testing for. If this is true, then it's outside. And if it's outside, then, you know, you're going to return that. That's what you're going to return, right? So this is what, if you're checking to see if it's outside or not. If this is not true, it says return not outside. That's what it's saying. So not outside returns whatever this thing is, okay? If it's true or false. And this is the simplest way of detecting if an object is inside or a point is inside of an AABB. Why do I care about that? A lot of times, the point that we're looking for is the center point of 2 objects, right? If you think about it, right? So we don't really care about 2 AABBs colliding necessarily. If one AAB's middle point is inside of another one, somehow we have overlap, right? So we can do that test as well. Or we can test other points. Capsule contains a point. Okay, so that's we have a line segment. Again, going back to that minimum distance squared, minimum squared distance, if you will. Right here, we have a capsule object. We have a contain method, and we're passing in a vector 3 point. Could be a vector 2 as well for 2D, right? And if you think about a capsule drawn in 2D, literally 2 circles and some kind of a line segment that has, you know, basically some volume. So, you know, looks like a 2-dimensional capsule, if you will. So that's possible as well, especially for 2D characters. 2D character capsules are awesome when it comes to things like platformers and all that kind of stuff as well. Very, very accurate for what we want to do. Okay, so we have this distance squared is equal to this, the line segment minimum square distance of the point. So that's what the distance is. We take the line segment and we find the minimum square distance, whatever that is. And then we want to just decide whether the squared distance is less than or equal to the squared radius. That's really it. If we have that, that point is inside of the capsule somehow. Okay? So again, think about that's why we did that whole line segment and the distance between the line segment and the points. That's why we did that test, right? In the beginning. We talked about that. Okay, this one, convex polygon contains point. Okay, so we have convex polygon as an example. And if you notice A, B, C, D, and E all add up to 360 degrees, right? Those are all the angles. And we have a sum of all these vectors. And we want to find if a point, you know, a 2D polygon contains a point. Okay, so here, let's say my pointer here is the point. Let's see how do we detect that? And there's a bit of a test. I'm not going to go through this one. Just more detection. But basically what we do is we take in a vector 2 object, right, as an example. And then we cycle through each of the points that are inside the polygon, and we can find that if it's close or not. And if it is, then we're good. One thing to note is this idea of, one thing I want to kind of zoom in on is this near zero thing, right? Why do I sometimes need to use this near zero? right? This is an important thing, by the way, near zero. Yeah, we have some weird floating point error sometimes. It'd be like 0.00003, right? That might be good enough, right? It's usually 5 decimal places. That's why we used to go like 0.0000005, right? That's good enough. It's close enough, right? Where we should have a collision at that point. I mean, it's not on the line, but that's what near zero means. We have some kind of thing that is almost like the value. All right. So we have functionality like that as well. And if we don't, we can create it. Okay. So once we have, that's the first type. The first type is point inside of this intersection, point inside of an object. Okay. Now this one is bounding volume test. When I compare 2 bounding volumes and their intersection, that's another way we can do it. So sphere versus sphere. Okay. I always look at sphere versus spheres like, I don't know, there was an old cartoon called Spy versus Spy. You know, you get a black spy, you get the black and the white spy, and they're kind of always fighting each other. And at the end of the day, that's what I look at when I say sphere versus sphere. I've got 2 spheres, sphere A and a sphere B, and then I want to find the squared distance between the 2 centers, right? I want to find the distance between those 2 things. Squared distance again, not square root distance, or not Pythagorean distance. And then I want to get the sum of the radii, right? So whatever the sum of the radii, and again, just like detecting two circles in 2-dimensional space, I'm comparing this in 3-dimensional space. Okay, how about AABB versus AABB tests? So again, what we want to try and do, let's see if I can actually zoom in here without killing everything. What I want to do is I want to have, you know, a couple of scenarios here. So there's this scenario where I have my A on the left side as an example, and you have, you're comparing A max X, so this is the max X, and is less than B min X, right? So this is less than this. We're just comparing 2 X's, yeah? Oh, how did that go away? I don't know if I can do both. I can't do both, right? I can only zoom or point. I can't do zoom and point, all right? Sorry, it's just multitasking for PowerPoint is bad. I don't know. Anyways, but if you notice the one on the top left, you can't see my pointer, but the one on the top left, and then there's the one on the top right, and bottom left and bottom right. There's 3 cases here, and they talked about these 3 cases are the ones we want to look at in terms of how we do a comparison between volumes. Once we understand this, right, depending on which case you're looking at, then you can move on to the code, which can look like this. I want to know if these two AABBs intersect. I have 2 bounding boxes. This is very, very practical, guys, right? This little thing right here. If I was only going to do this in 2D, it would be X and Y, and I wouldn't care about the Z, right? Here I'm doing 6 little comparisons. In 2D, I could do 4 comparisons, right? And then once I know if this is true, then we can see if the collision is true or false. And once I know that, I can detect these 2 things are overlapping. And we saw this very similar pseudocode last week, okay, but just in 2D instead of 3D. All right, how about sphere versus AABB? So we have a sphere and some kind of other kind of rectangular prisms kind of bounding box. This is interesting. So I have a minimum and maximum distance, and then I have some kind of A or B. And if you notice what A and B stand for is, where is the center of the sphere? Is it closer to the max or is it closer to the min? Once we start getting into that place, guess what we're looking at again? Line segments. We can actually detect the point in a line, right? Once we understand how to do that, we can do this. And we have some simple math to figure that out. I can find that, you know, the max of min X and the point X and 0.0f, which would be the Z coordinate we're looking for here. And then we can use the change in X, right? Where we try to find the maximum. We define the maximum of the X, and then point X minus max X. We find a maximum value. Once we figure that out, you can get into this minimum distance squared between an AABB and a point. And once I have those 2 things, I can figure out if the sphere and the point, because remember that point will be representing the center of the sphere. The sphere and the point are, if they're intersecting, once I figure that out, I'm good to go. I can figure out if those 2 things are intersecting. So sphere versus AABB test. Here's intersect, right? Where I can actually take the sphere and the AABB and I pass in the stuff we just defined earlier, which is the minimum squared distance, and then the sphere's radius squared. And once we find these two things out, we can detect if it's intersecting or not. Okay, so that is sphere versus AAB. How about capsule versus capsule? Again, another SPI versus SPI, right? Once I see capsule versus capsule, I'm like, hey, that's easy to figure out again. Because remember, a capsule is just a line segment with a radius. That's really what it is. So kind of very simple. We take in two capsules. We take the minimum squared distance between segment A and segment B, right? And then once we find the minimum square distance between these segments, we take in the sum of the radii. We add the two radii up. Radius of the first capsule, radius of the second capsule. And then we say if the squared distance is less than or equal to the radius, it's almost very similar to sphere versus sphere collision, except we also compare line segments, right? Once we figure this out, we're good to go. We know that one capsule is inside of the other one, okay? All right, line segment versus plane. Okay, so we have a line segment and we have a plane. Why would we care about that? Well, there are some good edge cases where the line segment is, let's say, the edge of a polygon in 3D, right? So I have an edge of a polygon and I'm colliding with the plane. Why would I care about that? For physics, super important. And a good example of that, if I have an icosphere, anyone know what an icosphere is? Back to Blender. Let's make an icosphere in Blender. When Blender wants to, behave. Okay, so we have a three-dimensional volume. I have a cube, but I want to add an icosphere. Let's add an icosphere. There it is. There's an icosphere. And by the way, the icosphere, I can reduce the number of subdivisions or increase it, right? So again, it's some kind of multiple, a polygon that looks like this. I can make it so that it's, yeah. Once I start going higher and higher, it's different. But the icosphere and a sphere, a regular UV sphere, are different. And I'll show you the difference. So here's an icosphere where you can reduce it down to a bunch of triangles, right? Here's a bunch of triangles. What if I add another one? Let's add a UV sphere. And here's the difference between an icosphere and a UV sphere. If I look at the, subdivisions between one or the other, you can see that they can both represent a sphere. This looks way more jagged, right? This is much more lower poly count, how many polygons there are, compared to this one. This one's way higher poly, right? Yeah, they're quads, and quads are always better. So whenever we're modeling, we want to model with quads, not triangles. Triangles deform weird, right? This is okay for different situations where we're not deforming the volume, right? Like if I'm using triangles, it's got to be something that doesn't move, doesn't change, right? We can still display this, no problem. And most likely what we're going to do is we're going to take the quads and cut them into triangles anyway, right? We're going to triangulate them when it comes to moving them, because when you're going to draw them on the screen, you're going to have a quad and you're going to cut it in half, right? You're going to make triangles, right? So let me just get rid of this one for a second, add it back in. You can also reduce the number of, and again, we're just talking about some basics here. So I can reduce the number of segments on let's move this to 16. Here's the number of segments, and I can, if this is a 16 by 16 sphere, it's much, lower poly again, compared to the 32 by 16 that I had earlier. One thing to note is the top of these objects, when modeled together, if I was going to go into edit mode, you can see that here we have a fan. This is bad, right? So I would convert this into something else other than a fan. You wouldn't want this situation, especially for an eyeball. If I was going to make an eyeball out of this, I'd be in trouble, right? Because what would happen is UVs, and by the way, U and V, is kind of a coordinate system that we use to map images onto volumes like this, right? Texture mapping, if you will. So if I take a texture map and I map it up here, what's the problem? It gets skewed because I'm stretching it and I'm squashing it in this area right here, whereas these ones are fairly consistent, right? And I can get a much smoother area here than here. This is really bad for if I was going to kind of texture map something, right? Because it's all triangles. So it'd be really hard to kind of put together a really cool texture. Imagine if I made a face with this thing compared to this thing, or I made this one the eye as opposed to this one the eye of the person. That would be really bad. This would be really low poly eye. It would look like a character from like the 1980s, and this one would look like something else. Yeah.
So what's the point?
This one?
Yeah.
Well, it accomplishes different things in terms of, remember, when you do part surface modeling, sometimes you have a need for something that looks like this, right? The other thing is that this one is divisible in half. So, for example, if I take this, and this is a little bit off topic, but hey, what the heck? If I take this and I put it into orthographic mode, so here's ortho mode, and let's just move this shape, oops, undo. Let's just move this shape out of the way, and this shape out of the way. So now we're in pure 2D. We're in orthographic mode, right? And if I was going to go into edit mode, and if I look at wireframing, right, for both objects, you can see that I can cut this object in half, right, by just using some kind of selection tool, like let's say something that looks like this. So I want to cut this object in about half. I can select half of the vertices and just delete it, right? Yay, half a sphere, right? And it looks pretty good, right? But what about this one? Can I cut this one in half? Nope. That's why we use it sometimes, because we want something that's not divisible that way. And it's a different object altogether. It's more of a matrix or node, than this, right? This is all even polygons. These are not even polygons. Some of the polygons are bigger, some of them are smaller, right? The surfaces. So depending on what you want to do, if you want to do organic modeling, you'd probably do it like this, with some kind of shape like this, starting off with an object. And this would be more used for other things like maybe some hard surface modeling or some very simple low poly shapes. Okay. But why did I bring this up? This wasn't the reason why I brought it up, because we talked about this idea of a polygon like this colliding with a plane. So if I have a plane, as an example, here's a plane, and let's just make the plane down here as an example. So there's the plane. It is an actual plane, not a it's not a line, right? So if you look at it now, if you look at this point right here, point, plane, right, as an example. We can also rotate this thing. Let's rotate it across the y-axis, right? So now we have an edge and a plane. Okay, let's check this out for a second. So here we have an edge, and we have the plane. And we want to see if there's a collision between the edge and a plane. Only one of the edges of this polygon is colliding, if you guys can see that, right? Potentially, not the whole polygon, not a whole face, just the edge. And this is a good case where we want to do this. So line segment versus plane. I have a line segment, which is the edge of a polygon, and a plane. I want to see if there's a collision. Sometimes we get into this. Why? Because I have a bounding volume around an object. As an example, I've rotated this bounding volume, maybe, and I want to detect if there's a collision. And this is one of those cases. Okay, and there's other ones too. And here's the code for it. So I'm gonna put the code up online as well if I wanted to do this kind of detection. Well, am I going to ask you to do this kind of detection on an assignment or a test? No. All right. So don't worry about this. In fact, your tests and your assignments are all going to be in 2D, right? Because that means you'd have to render things in 3D, and we don't want to do that. Okay. Line segment versus sphere. Okay, there's another good case where I have a line segment and a sphere. Why? So now it's back to that, a sphere test as opposed to a line segment. We also want to detect if it's intersecting. Why? Because now a line segment can be a ray, not just a plane. And so now, is the ray hitting this sphere? No. Is the ray hitting the sphere? Yes. It's just touching it on a particular, on this tangent. Is the ray hitting the sphere? Yes. It's actually crossing between this, this thing is being crossed twice. Yes. No, the tangent, and thank you, and intersections, secant, a secant line. Okay, that's what this is. Okay, so that's how it's used. And what we're using, if you notice what this is, b squared minus 4ac, it's what they call the discriminant, right? The discriminant, or the negative discriminant of the quadratic equation. That's what it looks like. If you look at this b squared minus 4ac is the actual discriminant, the thing that's underneath the square root sign, right, in the quadratic equation. So it's very interesting the way they do that. And of course, I have some code for that, which I'm not going to go over because, again, this is outside of our thing. I just want to talk about it, that there's ways of detecting the intersection between a line segment and a sphere. Okay. Line segment and AABB. Again, this is very, very common. This one we do want to talk about because this one is something that we can use in 2D as well, right? So we have a line segment from A to B, and we have this, bounding volume, which is AABB, and these are the three cases. Case A, where I'm not connecting. Case B, where I am intersecting, only in one area, and case C, where I've got a secant line that draws pretty much between, it intersects in two places. Okay, so that's the three cases, and depending on which case it is, case A, case B, or case C, we have the ability for us to detect this. Okay, so here's the test. For this particular one, we have the start and the end, and we have something called neg D, right? We're going to talk about this, as well as a vector, which is we're getting the reference to this vector as an example that's called out. Okay, so basically what we're going to do is this. We want to get the denominator, right, as an example in this particular case, which is n minus start. Again, this is mathy stuff. If the math is near 0 for the denominator, if it's near 0, then return false. So we didn't somehow connect, right? Else, if it's not near 0, and I mean somehow when we do this calculation, then what we want to do is we want to get the numerator, this ratio of with what we're comparing on. And what we're going to basically do is negative start plus the negative denominator, and then what we're going to do is we're going to figure out if it's true or not. And there's only one type. And notice when it says m place back, what this is doing is it's like, what's the difference between place back and push back? Does everyone know? If I have a vector, vector out. Yeah. Okay, so in place back is different than push back, right? In terms of the way it adds it on to the into the object. Okay, and that's really the test with the side of the plane. All right, if this thing has been hit by a line segment, start and end, where the start and end is the start and end of the line segment. Okay, and that's once we've got that, we can actually do an intersection between line segment 1 and AABB, right, where we pass in the information between one and the other, and I've given you the code for that. Okay, last topic we're going to talk about today before I let you guys go, and we go into, I'm leaving, we're stopping a little bit early because I want to talk about some other things like the exam next week and all that kind of stuff too. So we have dynamic objects. We have this idea of a bullet passing through a plane, and we talked about this briefly last time, this tunneling effect that we have of these, these bullets, something small object passing, you're going, traveling very quickly, and it's going through an object as thin as a piece of paper in this particular case, it looks like. How do I detect it? If this is frame 0 and this is frame 1, then we're going to miss the detection window, because what's happening is if it moves so fast that in frame 0 it's here, and then frame 1 it's over here, then we don't know, we won't be able to detect if it passes through this plane. And how do we figure that out? We can use something called a swept sphere, which we talked about kind of last week, right? And a swept sphere will basically be, let me bring this a little closer so we can see this one. This is interesting code. We have a sphere 0 and a sphere 1. Think about this as a capsule, again, going back to the whole capsule idea. And then what we have is, so we have Q0 and Q1 and some kind of out, which it says is T. And if you notice what T is, again, we use the discriminant to figure out where it's being colliding with on the sphere itself, because that's what we're doing. We're saying, hey, there's a swept sphere. Can we detect where the object is? We have these what looks like 4 spheres here, but there's really not. There's only 2. And notice that we're getting we're using this reference or dereferencing, a dereferencer to kind of get the kind of reference to each of the spheres that we're getting instead of creating or copying over new ones. Why is that? A lot of times we don't want to make copies because, especially if we're doing this on a frame basis, it's going to be very, very slow to do a copy and lots of memory, right? Where are copies made, by the way? Are they on the stack or on the heap? Make copy and I want to use it locally. Where is it? Stack, right? So I put a copy on the stack. So if I'm copying 4 spheres on a stack, right, that might be pretty heavy duty, right, in terms of a copy operation. I'm actually allocating memory temporarily, and then I'm also doing garbage collection on a per frame basis. That's really crazy, right? So especially if I have lots of these types of detections, these swept spheres on a regular basis, I don't want to do that. So, okay, so why 4 spheres, right? We actually brought it up into play last time where we have the first sphere representing the original where the bullet is right now, and another sphere of where the bullet's going to be, right? And then we have the other, the one sphere, which is at the top of the bounding volume, and another one at the bottom of the bounding volume. So we have 2 capsules here, which goes kind of almost like let's look at it in terms of a vertical capsule and another one that's horizontal. And we're kind of trying to find the intersection between 2 capsules, yeah. Why do we what?
Why do they take here on the bounding volume?
Why do we detect spheres?
And if this is a bounding volume sphere, why do they here
instead of a cube? Okay. A lot of times it has to do with the what's good enough again. Could you use a cube or an elongated prism? You could. If you really wanted to, you could do that. And now you're talking about intersection between 2 AABBs. However, AABBs are axis aligned, right? So it almost have to be like this, right? And bullets are almost never like this, right? Bullets are like this, right? You're shooting a bullet that's kind of going at an angle, right? So it's difficult to create an axis aligned bounding box. It would be almost like an OBB, an oriented bounding box like this, right? And that's way more difficult collision detection than swept spheres, right? That's why we presented here. So you have 2 swept spheres. They look like they're crossing over like this, right? Kind of like almost in a cross. And then you can detect whether it's connecting or not. Yes? Absolutely. The video is happening right now. We're actually recording the video, and I'm actually going to put this up as soon as we're done, right? Don't worry. I'm not going to, yeah. I know it's tough, especially when it comes to looking at code, like first thing in the morning, right? So, yeah, so again, what we want to do is we want to find these 2 bounding spheres, swept spheres, right? That go between kind of that connect, right? And if you look at last ones, okay, so this is bad. Take a look at this. The discriminant is using square root. Here we can't get away without using it, okay? And the reason for this is it's not just convenience. We're trying to find the discriminant. We're figuring out the discriminant of the square root, right? The discriminant is the square root, right? If you think about that, that's what it is, right? Once we find the discriminant, we can connect it. We can check to see where it says out t, and just to go through here, we've got this floating point object, right? And what we want to do is we want to figure out when we have our centers. So here's x and y, and what this is the difference between centers on the x-axis, right? And the y is the difference between centers on the y-axis, right? And what we're basically figuring out these differences between these 2, the 4 spheres, between one sphere and the other one, okay? P and Q and P1 and Q1, kind of thing, where P's and Q's are just different kinds of spheres, different spheres, right? So P0 and P1, let's say, would be the vertical spheres, if we're going to talk vertical, right? And then Q0 and Q1 are the horizontal ones, representing the bullet, okay? And that's how you'd figure those things out. Once you've got that, you get the sum of the radii between P0 and Q0, as an example. And then basically what you're going to do is you're going to solve, you're going to take the dot product of the x's, which is the P0 center and the Q0 center. So again, P0 and Q0, right, over here. you're going to get these A, B, and C's. Once you've got A, B, and C, now I can put together this, the discriminant equation, B squared minus 4AC. Remember, that's the same thing that we've got here, B squared minus 4AC, which is this line where it says float. I know you guys can't see my cursor, but it is laser pointer right here. B squared minus 4AC, this line right here, right, which is the discriminant. Okay. And once I have this, if the discriminant is less than 0, again, we talked about this, then there would be no collision. However, if it's not less than 0, now we check to see what the discriminant is. We kind of revamp out the discriminant. And then this out T is what we're returning, right? And it's the location of the collision. This is determining where the things are going to collide, right? So once we're into this part right here, where it says discriminant is equal to math square root, we detect if the location of the point, as an example, is greater than 0, greater than or equal to 0, and notice it says out T is less than or equal to 0. How's that possible? How can it be like 0? That's 0, right? Greater than or equal to 0 and less than, or if out is less than or equal to 0, but also greater than or equal to 0, what does that mean? It's 0, right? Then we were going to return true. Otherwise, we're going to return false. But why is this true? Because remember, out can be a very small number. And that's why, we want to try and capture that. So we can't just say 0. We can't say equals to 0. It's something that's maybe very close to 0, but not 0. And that's why we have to use this equation. Okay? Otherwise, it's false. If it's not close to 0, right at the point, then there's no collision.
Is there no way to use that not close to 0?
Yes, there is. Yes, there is. So you can replace this with something that looks close to 0. All right, so that is the different kinds. So what did we cover today? We covered 3D collision. We talked about 3D collisions and the formula that we're going to be using. And I've given you some patterns that we can use for your collision detection. So we spent 2 weeks talking about collision detection. Guaranteed some kind of collision detection thing is going to be on your exam, which is going to happen at 2 weeks from now, right? Because we've talked about it a bunch of times, right? Collision response, I'm going to cover 2 things with the collision response next week. I'm going to cover the physics behind it. So we're going to talk about momentum and energy of a system in terms of how do I transfer energy, and I want to do energy conservation. And then 2 types of collisions, elastic collisions and non-elastic collisions, right? So I have elastic collisions, bounce back. Non-elastic collisions, they don't bounce, right? They just they crumple more than anything else, right? So 2 types of collisions. Okay, so that's next week. So next week is a kind of a key week in terms of response, right? And there was 2 ways I could have gone about this. I could have said, okay, I've already covered detection. Let's just do 2 weeks of response. But I think detection is a lot of times more important, okay? Why? Because in real video games, we do, okay, I can detect a collision, and now I can explode the object. Okay, it's gone, right, or whatever. Most of the time, or I reset the object. By the way, in lab today, what I'll be doing with you guys, for those people who are coming to lab, and this whole week, is I'm going to be building these enemies. So last week I built a player game object. This week I'm creating enemies, and I'm also adding I'm creating a new template that I'm a 3rd template, so template version 3, right? I keep on building the templates a little bit bigger, right? So that way it includes more stuff. And this week I'm going to give you a template that includes sound support as well as frame support that is regulated, right? So it's not going to be just like I want to run my while loop to infinity. It's going to be like a fixed frame rate. We talked about this last week. Some people ask me, hey, how come we're not running a fixed frame rate? And I'm saying, wait, right? One thing at a time. And so this is the week we actually talk about fixed frame rate and then how to do that. So I'm going to give you this new template this week, which I have ready. And what we're going to be doing with it is also talking about how do I do input, different kinds of input with SDL, which is I'm going to use the mouse input for now. And I'll talk about how you can do input detection for keyboard as well. Again, we're not making full games, right? But we can create some structures that we can use for our assignment. All right, questions around detection in 3D? Yes. The very beginning, like way back. All right. So sure, I can do that. You're talking about way at the beginning, where the first thing we talked about was the line segment. And that is here. This one? Oh, this one. Okay. Yeah, this is the minimum square distance. Okay, let's look at this. Sure. Oh, case 3 down here. Okay, you're not sure how to do that? Right.
How can you calculate the vector? The P is the vector or between the point A and B, right?
Well, if A and B fail, if it's not less than, and if it's not greater than, it must be in the middle. That's the thing, right? Yep.
Which is projectional function of segment of A and B.
So the dot product between AC and AB, right? AC, AC, and AB, right? So we have this. We have a projection of AC on AB. That's what we're doing, right?
The vector of the line A and B, it should multiply the scalar multiply by AB, so the AB should be normalized.
Oh, I see. Should we normalize it? A and B? Scalar times AB. Yeah, we'd have to normalize it, but there would probably be a norm. So what you're not seeing, remember this is pseudocode, right? So you're not seeing here is, don't be confused, because what we're saying here is AB is actually a vector, right? And in this code, vector 3 is not vec3 like we were using in class, right? Vector 3 might have an overloaded multiply operator that automatically normalizes the vector for you, right? I'm just saying, right? You don't know what's happening in the background, right? So, but I agree with you, because if we don't normalize, what happens? What does normalization do, by the way? What is it? It's actually a yeah, it turns it into a the unit vector, right? 0, 1, right?
Like make the scalar function in between 0 and 1.
Yes, as opposed.
If you don't normalize, the scalar can be like equal to 1 or
yes, and that would be bad. Yeah, that would be bad, right? So we need to make that scalar something so we have to normalize the dot product, is what you're saying. Yeah, it makes sense. Yeah, it makes sense. All right, and then this is good. This is good that you thought about this. But again, one thing to check is actually create some vectors yourself and use the formula and see what you come out with the scalar. Actually output those values from mathematical perspective. But I agree with you, because if you get a dot product that is, we're trying to figure out the t value, basically. Yeah. That's what we're trying to figure out, the t value between the 2 points. So yeah, normalization is a good thing. Okay, any other questions or any comments about this kind of stuff? All right, so that's really it for me. So again, just before I go, one thing to note is definitely today, at the end of the day, you will have your assignment 3. Okay, assignment 3, I'm looking at probably making it only 2 questions. Okay, I'm just telling you, because remember, you're going to have to make two separate scenes. And what are 2 separate scenes in C++? 2 different programs, basically, is what I'm going to ask you to make, right? Program A and program B, which means you're going to have now, if you're smart enough and you create a scene class, great, scene switcher and all that kind of stuff, not asking you for this. For me, it's as simple as making literally 2 copies of the template, copy A and copy B, 1 copy to answer question A, the other copy to answer question B, and you make a scene for one and the scene for the other. That's all I'm looking for.
This is for the exam.
No, this is for the assignment 3. It's coming up. Yeah.
Is the final we have assignments not given?
Sorry?
Is the final we have assignments that you don't have any?
We have an exam for the final.
The exam isn't going to be the same format as the other.
No, yeah, it'll be a coding exam. Yeah, it'll be practical. Yeah.
Is this assignment a group
Yes. Yeah. For sure. Yeah.
Will the assignments need player input? Or will
Yes.
it just be a simulation?
No, it'll be a player input. You have to move. So the first question that I'm putting together is you have a bouncing ball, and the bounce you have some kind of brick that you're controlling with your player. When the brick hits the bouncing ball, it'll gain momentum or energy, and then the bouncing ball will either every time it hits the wall, it's going to slow down. That's what I want you guys to do, right? Every time it hits the paddle, it speeds up, right? So I want to see that simulation, right? It'll be due the last week. It won't be like it'll be the very last week of class on the Friday, like the last week, right? So you have a couple weeks to do it. It won't be too crazy. That's what I'm saying. I'm probably going to make only 2 questions. I've almost completely finished it. I just want to make sure I want to give all the details where the marks are going to come from and stuff. So there's no question around how much it's going to be and how difficult it's going to be. There really isn't that difficult. If you have 3 people working on it, I mean, it should be pretty straightforward, right? The second question is all going to be around bullets. I have all these bullets falling like rain, right? 10 bullets, let's say, falling like rain on the screen. And you have a player ship. The player ship, every time it gets hit, makes a sound. But it can only make a sound from each bullet once. That's it. That's probably going to be what your assignment's going to be. It's pretty straightforward. I'd probably want you to reset the bullets. So the bullets are reused all the time. So you're not going to make, bullets with memory leaks everywhere, like 10 bullets every frame. It's too much, right? The bullets will start off at a random X location on the top of the screen, right? Some extra work. So question 2 and question 1 are very similar, but one has more to do with energy. The other one has more to do with collision detecting bullets, only having a single collision once. Very simple stuff, right? And if you can do that in 2D, you can do that in 3D. All right, so that's going to be your assignment. I'm almost done putting the details down, and then I'll give it to you guys, and you can start it. Yep.
Would like the bullets get destroyed after?
No, reset. Let's reset them. Yeah. Once I start going destroyed, now we're doing memory management. I don't want to do memory management. That's not the exercise, right? So it's resetting. We'll reset the bullet off screen somewhere, like -10,000, -10,000.
Once it hits the ship, or if it goes off the bottom of the screen.
Correct. Yeah, that's right. That's right. So there's only ever 10 bullets, ever. Nice and easy, right? But the reason why I want to do this is because if you can do it with STL, and if you can do it with versus a ship that has texture on it or whatever, and there's 2 different bounding volumes, right? You have some kind of circle that I'm probably going to get you to do on the bullet, and an AABB. So circle versus AABB, right? There's lots of stuff you can do. So I'm leaving it to you as long as you can do proper collisions. So again, it's simple tests, right? It's a very simple assignment, but it's good enough to get you guys your hands into the code. That's all I want you guys to do. It could be something that's very simple to do. I'm not asking for complex collisions. A complex one would be something like, and I was thinking about this, you have a car and you drive the car into a wall and, what happens? What do you do? Does it collide? Does it bounce off? How much energy does it lose? That kind of stuff. But the ball does that. The first question would do that, right? Because it's almost like I have a ball and I'm projecting the ball onto the wall, almost like brick breaker, right? And then it loses energy. It doesn't gain energy. It loses until it slows down and stops. What happens when the ball stops, right? What do you do with that, right? That's the thing that you have to think about. Like if you play the simulation long enough, the ball should stop moving, right? Because it's going to lose energy, right? So how does that work? I'm not going to ask for gravity, no gravity. Okay, so it's like top down. Okay, once I start going gravity, then we're talking real physics, and you have to make your own physics engine. No, yeah. Yeah, that's exactly it. And then you're getting some energy, and then the energy is going to be reflected in a certain place. And we'll talk about that next week, how to do response. But you can look it up. I'll post the slides earlier, and then you guys should be able to take care of that, no problem. Okay, anyone else have any other questions? So assignment 1 and then final exam. Final exam, if you know how to do assignment 3, then the final exam should be something like that. Well, I'll do some other kind of collision detection response. So it'll be one thing, one feature to do. Use the same template, but you'll do it on your own. So without anybody else. Okay, one thing and then you're done. And then that's your exam. Okay, so it should be fairly straightforward. Like I said, if you're attending classes and you've done everything so far, then the final exam should be no problem. Okay, like seriously. All right, any other questions? guys, thank you so much. We'll see the rest of you guys in the lab today and this week. Okay, and I'll try and broadcast the lab on Friday. Yeah. Yes, there is.